there, and welcome to a Calculus 2 video where we are reviewing our Calc 1 integration. This video specifically will cover a little bit of trig and also some of the definite integrals using that fundamental theorem of calculus. So one thing that we should recall is, what is the fundamental theorem of calculus? So it had two parts. This was one of the parts. So when we look at it, we're anti-differentiating from a to b, so now there will be bounds. This was our definite integral, and so you'll notice that that lowercase f did turn into capital F because that is the anti-differentiation of that function. And then you're going to take your endpoint, so upper bound value in there minus lower bound. So, all right, let's see how this works, and these are going to use substitution in some way. So with definite integrals, we do have to be really careful about the fact that we are in single variable calculus for all of Calc 1 and Calc 2. So we have to make sure that if our bounds are 0 to 2, our function is in terms of x. That was the derivative in terms of x, so I'm going to anti-differentiate in terms of x. All of those pieces sort of match. So once we change to u, we will also change our bounds. So what I mean by that is, let's start with the good old-fashioned u substitution. So I think we're familiar, since we had the previous video, that our u is the innermost piece, right? Or if you were doing the derivative of this integrand and you were going to do the derivative, you would need chain rule because of this 1 plus 5x. I have a function raised to the 10th, so a function inside of a function. So that shows me what the u needs to be. So then du is 5 dx. And so we talked in the last few videos here how I will multiply a 5 in, because then there's my 5 dx, and I will put a 1/5 out front. So what this actually looks like is I have a 1/5 out front. I'm not going to put my bounds on just yet. I'll fix that in a second here. This 1 plus 5x is really u to the 10th, and then that 5 dx becomes du. And I think I can integrate that no problem. So what we're going to need to get a little bit better at in Calc 2 if we weren't in Calc 1 is, I think it's going to be very, very helpful to change our bounds. So for example, our bounds started at x equals 0. So I'll say if x equals 0, I'm going to figure out what u is. And also, if x equals 2, which is my upper bound, what is that u value? And the reason we're doing this, and the reason I'm being so specific about it right now, is that we're going to have problems that maybe start with x, and we're going to insert trig later on down the road, and we'll go to thetas. And then maybe we'll have to use a u substitution from there. So I will have changed the variable from x to theta to u. And it's just really helpful if you change the bounds along the way, because then you have the numerical value for the bounds and you don't have to go all the way back to your x's in the end. Well, this is actually a very simple process here, because you have the relationship between u and x. So if I know x is 0, you're putting x equals 0 into that statement, u equals 1 plus 5x. Again, x is 0, so u is a 1. So my lower bound turns into a 1 in terms of u's. And then if x is 2, u is going to be same relationship here. It's 1 plus 5 times that x value, and now my x is 2, so the upper bound here would be 11. And now the benefit is that I can integrate this. I do get 1/5 u to the 11th over 11. I'm going from 1 to 11. That is coincidental. And let's see. I'll pull the 1 over 55 out front here. And then it's just going to be this u to the 11th. So it'll be 11 to the 11th minus 1 to the 11th. That is a very, very large number. And even if you try to calculate that on your calculator, you're going to get something like 2.85, etc., E11, just for the 11 to the 11th part. So this is a fine and acceptable answer. There's no need to write out that, huge, huge number. Okay, so let's do this again. Let's do it with ease. E, E, E. All right. So I'm going to see the inside of my function as my u. And then let's make sure u substitution is going to work, because again, don't bother changing your bounds until you know that u substitution is the technique that is going to work for this integral. So my du, well, derivative of 1 is 0, derivative of e to the x is itself, so that's e to the x dx, and that's exactly what I have. So this integral appears to turn into antiderivative of the e to the x dx becomes the du, and the inside becomes square root of u. You could also write that as u to the 1/2. Well, I need to change my bounds because again, we are in single variable calculus. So if x is 1, that's my lower bound. I'll try to figure out what u is. And if x is 2, I will substitute that in and see what u is. And again, you're going off of that relationship equation that you wrote from the very beginning. You said u has to be 1 plus e to the x. Okay, well if x is 1, then this becomes 1 plus e to the first, or just 1 plus e. So that's my lower bound. That is exact, so leave it. And then if x is 2, u is 1 plus e squared. Again, that's exact, just leave it. Okay, so when we anti-differentiate u to the half, I do get u to the 3/2 times 2/3. I'm going from 1 plus e to 1 plus e squared. And then I'll put my bounds in. I don't need to go back to x's, right? The whole point of doing this is that you don't have to go back for x's because now everything is in terms of u. So I have that 2/3, and then here's my upper and lower bounds. So I'll put in the upper bound first. 1 plus e squared to the 3/2. And I'm going to leave the 2/3 as a coefficient of everything. So you'll notice I just put these brackets here, because then here's my capital F of b, right? My antiderivative at my upper bound minus antiderivative at the lower bound, which will be 1 plus e to the 3/2. Now, if you're wondering what happened to the plus c, if you did put plus c here, what you would have noticed is you would have had a plus c here and a minus c here after you distributed the negative, and plus c minus c add to 0. So it's sort of like taking this area, and if you shift the whole area up 4, the area itself isn't necessarily changing. Okay, the other thing I want to mention is that this answer is exact and it's done. You would never distribute that exponent in because you have a binomial here. So you are done, and this is what the answer looks like. Don't round it unless it says to round. All right, let's talk trig for a little bit. And let's think about some trig integrals that come from u substitution. So I think in Calc 1 you should have seen the antiderivative of tangent x. Now there is no derivative that gives us tangent as an answer. And let's go over here. By that I mean, if I look at the 6 trig derivatives that we should know, so the derivative with respect to x of sine of x, we know to be cosine of x, which means the antiderivative of cosine was sine. So the derivative with respect to x of cosine x, we said was negative sine x, and you should be able to fill in this chart relatively easily, right? These are our Calc 1 derivatives. So the derivative with respect to x of tangent x was secant squared x. Derivative with respect to x of cosecant, remember all cos are negative, so I had the derivative of cosine being negative sine, derivative of cosecant will be negative, and the derivative of cotangent as functions are negative. So the derivative with respect to x of cosecant x is negative cosecant x, cotangent x. Secant x is secant x tangent x, and then derivative with respect to x of cotangent x is negative cosecant squared x. So what I mean by what I just said earlier about tangent is none of these answers are tangent, which means organically I can't just say, oh, well, you know, the antiderivative of negative cosecant x cotangent x, well, organically that's cosecant x because the derivative comes from that. But I don't have an answer to a derivative that's tangent. So, okay, how else can I do it? Well, tangent is really sine over cosine. So if I rewrite it like this, maybe this makes sense to you. This just comes from u substitution now. Remember we said when we have some rational expression or fractional, sometimes we can just let the denominator be u and see if we can get things to work doing that. So if I do that, u is cosine of x, so du would be negative sine x dx. And if I multiply in a negative and out a negative, then I have exactly that. I have negative sine x dx, that would be my du. I have cosine x on the bottom, which would be my u. So my antiderivative looks like opposite of du over u. So that is negative natural log of u, and my u was cosine x. This was an indefinite integral, so don't forget your plus c. Now, one natural log property that we might remember, so we'll go off to the side and see if this is something that you remember. If I have 3 natural log of x, that was the same thing as natural log of x cubed. And that was because this is natural log of x plus natural log of x plus natural log of x, right? So I have 3 natural log of x, that'd be 3 of them added together. Well, when you add natural logs together, remember natural log just solves for an exponent, so they are representative of your exponent properties. So when you're adding natural logs together, they already have the same base, so you keep that same base, so it stays natural log of x, and it becomes the product. Because again, if you're thinking that they come from exponent rules, you're 100% correct. When you're multiplying with the same base, add your exponents. And since each one of these is representative of an exponent, you add those together. So again, that's where the natural log of x cubed comes from. So we just kind of learned it as this coefficient of natural log becomes this exponent. So if that's the case over here, I'm going to look at this as negative 1. This would be the same thing as natural log of this cosine of x in absolute value bars raised to the negative 1. And in the previous video, I did talk about trig being raised to a negative exponent, and we don't often write that because then we get it confused with inverse functions. So the reciprocals to the negative 1 means reciprocate. We gave a name. So this is really natural log of secant x. And the reason I'm going to say that's huge, you could absolutely memorize it or know it or derive it with the negative 1 in front or as a coefficient of natural log of cosine x. But what I think is a little bit more powerful is if you can recognize the relationships between tangent and secant. I think that would be really helpful long term for Calc 2. Their derivatives are each other, right? All tangents and secants go together, as well as their Pythagorean. So tangents and secants will always kind of go together, which is what you're going to see in the next one as well. So that's why you're going to see I wrote it as 2 different ways here in the box below. You can certainly just know it as natural log of secant, or you can have that negative natural log of cosine, again, plus c. Okay, but secant gives us a little bit more problem because if I try to do a rewrite here, this is 1 over cosine x, right? Secant is reciprocal of cosine. So I can't do u du because if my u is cosine x, My du would be negative sine x dx. Well, I have the dx piece, that's fine, but you do not have the negative sine x. And you can't multiply in a function and multiply out a function because you can't pull a function out of the integrand like that. So that's not going to work. So, okay, what else? So I'm just going to leave it as secant, because that rewrite didn't seem to go very far. Now, I just got done saying how related secants and tangents are. So let me go over to their derivatives real quick here. So derivative of tangent being secant squared, and derivative of that secant of x is secant x tangent x. Okay, well also, if we know our Pythagorean identity that we start with, the basic one, sine squared x plus cosine squared x equals 1, and if I take that identity and divide every single term by cosine squared, I'm going to get an equivalent identity here, but using different trig functions. So sine squared over cosine squared gives me the tangent squared x, plus cosine squared over itself is 1, and the reciprocal of cosine squared x is secant squared x. So again, here's tangent and secant being related to one another. So back to this antiderivative. All I really have is secant. Well, let's try to manipulate something in, and this is something in Calc 2 that you're going to have to get better at. That might be the most unfamiliar part of Calc 2 at the beginning, is I'm going to manipulate in what I want and see if it makes it any better. And as long as you're multiplying by a factor of 1, you're not changing the value, you're just changing the way it temporarily appears. So for example, if I multiply by secant x plus tangent x over itself, let's see how or why that might help us. Again, don't forget your dx because that's your variable of integration here. So I'll distribute the numerator. So now it's secant squared x plus secant x tangent x, and now I at least have a little bit more to work with because at least I have functions in both my numerator and denominator, whereas before, if I just do a rewrite of secant of x, I only have 1 over cosine x. I didn't have necessarily a sine, cosine, tangent, etc. function in that numerator. So I'm going to go with the same philosophy we went with before, which was try to let your denominator be your u. So I have a rational expression here, rational integrand. Just try letting your denominator be your u. And then let's see if it works. Let's see if our du is here. So the derivative of secant x, we just looked at that a few minutes ago, right, is secant x tangent x plus, I'm going to put this all in parentheses, the derivative of tangent x is secant squared x, and this whole thing is dx. Well, take a look at your numerator. Secant x tangent x, ooh, there it is, secant x tangent x, okay. Secant squared x, secant squared x. You're adding, order doesn't really matter. So what you formed without even maybe realizing it is du over u, which would be natural log of the absolute value of u, of course, plus c, and I will put in my absolute value of that u, which was secant x plus tangent x plus c. So certainly, do some people just memorize, right, going from here to here? Sure. But what I want you to make sure you know is that you can always go back and just derive it, just multiply by 1. So you're going to multiply by secant x plus tangent x over itself. Now I'm going to show you one more without doing it and see if it makes sense, and you're certainly welcome to try it yourself. So antiderivative of cosecant of u with respect to u. This one has a few different ways that you can represent it, so try that one on your own. Okay, but it should make sense to you that cosecants and cotangents go together just like secants and tangents. All right, so let's try just a couple of these and then we will move on here. So tangent of 5x dx, I can see that I have a 5x function inside of the tangent. And if you wanted to rewrite it as sine of 5x over cosine 5x, you certainly can. Your angle has to be the same in order to rewrite those. Okay, so then I will let u be this cosine 5x. So then my du is negative 5 sine 5x dx. So hopefully that derivative is okay. That was a Calc 1 derivative there. All right, well, if I multiply the numerator here in my integrand by negative 5 and outside by negative 1/5, you're going to have exactly what you need. So here's negative 1/5, antiderivative of du, right? I should have probably shown the negative 5 here and the negative 1/5 here. So I have du over u. That does make natural log of absolute value of u plus c, and I will put my u back in. U was cosine of 5x. Now, do you have to go through all of this part? No, not really, because you could have said, ooh, I know the antiderivative of tangent of a function would be natural log of secant of that function, but you do have to account for u substitution. So I would have to say, oh, in that case, u is 5x, so du is 5 dx, so I would have to multiply in a 5 and out a 1/5, and that's where that positive 1/5 would come from. Again, if you have to multiply by 5 for the derivative, you're going to end up having to divide by 5 for its antiderivative. So a couple different ways you can write that. Okay, so I think I proved, the antiderivative of secant to you, but let's just see if this is in fact a secant antiderivative or integrand, because again, once you do u substitution, sometimes things change. So let's let this 2x squared be our u at first. And the reason we're doing that first is because I can really see that I have a function inside of another function, and truly I can always take secant of u off to the side and figure out that antiderivative. So u is 2x squared, du is 4x dx. So I'm going to move this 7, and I'm going to put a 4 in and an over 4 out. Okay, so now what I see is 4x dx, right, becomes that du, and then it'll be secant of u. So let's see what we've got here. So I have 7/4 on the outside, it's pretty light, and then I have that 4x dx will become that du, and I just have secant of u. And if you know it, oh good, this is 7/4 natural log of secant u plus tangent u plus c, and you've already done all the u substitution, all that kind of stuff. Then you're ready to go with that antiderivative. Or you can multiply by secant u plus tangent u over itself. And I'm just going to put back in now what my u was. And so there I have that 7/4 natural log, don't forget your absolute value bars, secant of the angle 2x squared plus tangent of the angle, which is 2x squared, close your absolute value bars, plus c. So I hope this helps get you started with some of your trig integrals and u substitution stuff with trig integrals, but also with some of your definite integrals or definite integration. And thanks for watching, and I hope you found this video really helpful. Have a good day.